Swayam Prabha. Digital India. Educated India.
We are going to continue our discussion on crystal structures of different ceramic compounds. Last time we have started preliminary discussion on silicates, the silica bearing compounds. We will come back to that discussion a little later. However, before that let me go back and discuss some of the features of the crystal structures which I have not discussed so far. The very first thing we want to discuss is a consolidated picture of what we have already discussed, that is a list of different compounds, primarily oxides, some sulfides maybe, and their crystal structures. We can classify them according to the formula of the compounds, their complexity of the structural features, and then the coordination numbers and so on. Some of these structures we have already discussed. Rock salt structure we have discussed its basic features. What we are presenting here is a consolidated picture of all the different oxides we come across and their structural features. So, the simplest form or simplest structure type is actually rock salt, and its general formula is basically MO, a bivalent metal with oxygen. And in case of rock salt structure or sodium chloride structure, as you have discussed earlier, is the basic anionic packing, it is a closed packed structure of FCC, that is face centered cubic or cubic closed packed structure. We discussed about the coordination number, either cation or the anion, and what it is presented here, what is the coordination number of the cation vis-a-vis the coordination number of anion. So, it happens so that in rock salt structure both cation and the anion have a 6-fold coordination. We also mentioned earlier that there are a skeleton of oxygen ions and the interstitial positions are primarily occupied by the cations. So, there are octahedral sites as well as tetrahedral sites. For each oxygen atom there are 2 tetrahedral sites in the structure and 1 octahedral sites. This all octahedral means all the available octahedral sites are occupied by the cations in this particular structure. And the examples of these kind of oxides we briefly mentioned, this is magnesium oxide, calcium oxide, barium oxide, strontium oxide, iron oxide, nickel oxide, manganese oxide, cobalt oxide, cadmium oxide, etc. So, all these oxides of the general formula MO normally crystallizes or have the rock salt structure. Next, we also discussed this particular structure is the cesium chloride structure, and of course, there are not too many compounds or there are hardly any oxides which has this cesium chloride structure, but for complete sake of completion this is a simple cubic. This is only one of the rare compounds having a simple cubic structure, and formula of course is CaCl, and in this case the cation having a 8-fold coordination and also the anion. Anion and cation both have this 8-fold coordination, right, and all the cubic sites are filled up. So, because both of them have the same coordination and it is a simple cubic structure. So, it is a cubic coordination. Okay. So, all the cubic sites are basically filled up by either cesium or the bromine, or in this case another compound is cesium iodide. So, this is one simple structure type. This we did not discuss earlier, but the structure type, there are many, some oxides do crystallize in this particular structure. This is zinc sulphide. Okay. Zinc sulphide in fact has two different polymorphs. One is called zinc blende and the other is called woodsite. The basic difference, the main difference is here. The packing in one case, or the symmetry in one case is a face center cubic. It is also a closed packed structure, as also the HCP. Both HCP and FCC has the closed packed structure, but one polymorph has a face center cubic structure, another has a hexagonal structure. Otherwise, they are all same. The anion and the cation both have 4-fold coordination, that means tetrahedral coordination, both in the case of zinc blende structure, the cubic structure as well as the hexagonal structure. And in both the cases, half of the tetrahedral sites are occupied by the cation. Okay. Half of the tetrahedral sites are occupied by the cation, because as you can see, the ratio of the cation and the anion is same, and the tetrahedral sites in a closed packed structure is actually double the number of oxygen or anions. So, only half is filled up, and the examples are zinc oxide, zinc sulphide. This is also zinc sulphide, one form of zinc sulphide, it is called woodsite, another form is zinc blende. Beryllium oxide crystallizes in zinc blende structure. Silicon carbide, one of the carbides commonly used in ceramic, particularly structural ceramics. Again, just like zinc sulphide, it has two different polymorphs. Silicon carbide has the cubic structure as well as the HCP structure, the hexagonal structure. Zinc oxide has a hexagonal structure. So, this is the another group of oxides, quite important oxides, having this either zinc blende or woodsite structure. Fluorite we have discussed earlier, calcium fluoride, the structure type is calcium fluoride and the mineralogical name of calcium fluoride is actually fluorite. It has a simple cubic structure, similar to some extent similar to cesium chloride. However, the coordination numbers are slightly different. For the cation it is 8-fold and for the anion it is only 4-fold. Okay. So, this is different compared to the cesium chloride structure. Half of the cubic sites, that means the 8-fold coordination sites, are being filled up in the fluorite structure. So, in fact, all the cubes or body center of the cube is not filled up, only the alternate sites, alternate cubes are filled up with the cations. Okay. And therefore, you have a large number of oxides, all of them are of MO2 type of oxides, MO2, ZrO2, CEO2, thorium dioxide, uranium dioxide, hafnium dioxide, and a host of this is praseodymium, and then you have host of rare earth oxides. Many of the rare earth oxides do have this fluoride structure and they have certain important properties which will be discussed later. Then in addition to fluorite, you have another structure type which is called antifluorite. If you look at the chemical formula of these compounds, one is CaF2, whereas the other is M2O. Okay. So, these are, you can see these are monovalent of metals like lithium or alkali metals like mostly lithium oxide, sodium oxide, potassium oxide, rubidium oxide. So, all these do have a so called anti-fluoride structure, and this is not simple cubic, this is FCC, close packed cubic, and this is different, this is just the reverse of this. Here the cation has a 4-fold coordination, whereas the anion has a 8-fold coordination, and all tetrahedral sites are filled up, which is quite obvious. In the fluorite, because of the particular formula, only half of the cubic sites are interstitial sites are occupied, whereas here all the tetrahedral sites are occupied because the ratio is M2O. Okay. So, there is a double the number of oxygen, the metal cations is double the number of the anions. So, that all the tetrahedral sites are actually filled up. To continue with this list, we have a rutile structure. This is the formula MO2 we have discussed earlier, and the type of compounds which crystallizes in this particular structure is TiO2, SNO2, GeO2, germanium dioxide, manganese dioxide, TiO2 again. I think there is a mistake, it has been repeated, and it should be tellurium, this tellurium dioxide. Okay. So, this is a distorted FCC structure, it is not a completely or exactly FCC, or it is not a cubic. In fact, we will see the symmetry is towards tetragonal, not FCC, but for our purpose at this point of time it is FCC, and coordination number of the cation is 6 and that of anion is 3. Half the octahedral sites are occupied in this case. Corundum we also discussed, and the chemical formula of the structure type is M2O3 sesquic oxides, and this is HCP, the symmetry is hexagonal, cation having a coordination number of 6, whereas the anion has a coordination number of 4, and only 2/3 of the octahedral sites, 2/3 of the octahedral sites are occupied by the cation, because of the formula here it is 3:2. So, you have only 2/3 and rest 1/3 is vacant, and the oxides which actually crystallizes or have this particular structure is Al2O3, Fe2O3, Mn2O3, Ti2O3, Cr2O3 and so on. Next, the complex oxides, we discussed both of them in the last class, and they are, the general formula is AbO3, and you had a cubic structure, cubic close packed or face center cubic in other words, and they have 3 different elements here. One is the one anion and 2 cations. So, the coordination numbers here is 12, 6 and 6. Okay. So, one of the cations has a 12-fold coordination, whereas the other has a 6-fold coordination, and the anion has a 6-fold coordination. Half the octahedral sites are actually occupied in this particular system. Okay. And in fact, this is a very important group of oxides having many different functional properties, we will discuss them later, particularly electrical properties. Many of them have very interesting electrical properties. You can even modify the electrical properties, and most of them are known for their high dielectric constant material. Barium titanate, strontium titanate, cobalt titanate, barium zirconate and barium stannate. Different kind of basically titanates, zirconate and stannates, most of them have this perovskite structure. We have 2 varieties of spinel structure, and the general formula is Ab2O4. Again it is a cubic symmetry, cubic close packed, and the ratio of the cation and anion coordination numbers not the ratio, they are actually coordination numbers of different ions. Cation is 4 and another cation is 6 and anion is 4. So, you have two different cations occupying two different sites, okay, because you have tetrahedral site and octahedral site. In perovskite there is none of the tetrahedral sites are occupied, whereas in spinel both the tetrahedral and octahedral sites are occupied. 1/8 of the available tetrahedral sites are occupied by A atoms and half of the available octahedral sites are occupied by B atoms. So, that is the what we call the direct spinel structure, and the examples are magnesium aluminate, iron aluminate, zinc aluminate and zinc ferrite. Okay. So, these are spinel structures with this kind of distribution, A and B distributed between tetrahedral and octahedral sites. The last variety in this series is inverse spinel, and the chemical formula or general formula is BaBO4. Here it was AB2O4. Incidentally, A is a divalent and B is trivalent. Here A is divalent, B is tetravalent. B here is a trivalent and two of the cations have been distributed between octahedral and tetrahedral, and A has gone inside the tetrahedral octahedral site. So, what has happened, B has come out from the octahedral to the tetrahedral. B was here in the spinel structure, normal spinel structure or direct, or it is actually sometimes mostly called normal spinel, not direct spinel. In the normal spinel structure, it is actually B atoms are in the octahedral sites, whereas in the inverse spinel B atom is actually distributed between octahedral and tetrahedral. So, half of B atom is occupying 1/8 of the tetrahedral site, and in the half of the octahedral available sites, A atoms are there plus half of B. So, there is a redistribution of the A and B atom B ions between the tetrahedral and octahedral sites, and the examples are iron magnesium ferrite, iron nickel ferrite, and then iron, in fact it is not iron, it is manganese ferrite, it is nickel ferrite and magnesium ferrite, and then of course there is another titanate is also there. Okay. So, magnesium is on this side, also on this side, and titanium it forms a titanate. Okay. So, these are the different kind of oxides available to us, and most of them are used for different advanced applications. One of the major oxides is zirconium dioxide, ZrO2. It has many different important properties which will be discussed later. So, it may be worthwhile to know a little bit about the structure of this particular oxide. I am trying to give little bit emphasis on the zirconia structure. Zirconia ZrO2, we have seen that just before this slide it was indicated that zirconia has a cubic fluoride structure, but all zirconia do not have the cubic fluoride structure. We have a cubic modification. So, this is the distribution of atoms so far as the cubic fluoride structure is concerned. So, this is stable at a very high temperature above 2200 degrees centigrade, okay. Whereas, room temperature zirconia has a monoclinic structure. So, there is a not so symmetric structure, it is a distorted structure. We will discuss about the different symmetries in a few minutes. So, you have zirconia has three different polymorphs. One is monoclinic and is tetragonal, and then the other one is cubic. This is the low temperature modification, room temperature to about 1100 degrees centigrade. From 1100 degrees to about 2200 degrees centigrade, this particular structure is stable, that is tetragonal, and then above 22 it becomes cubic. So, higher is the temperature, the symmetry becomes more regular, or it becomes, the structure becomes more symmetric. That is the normal tendency in any polymorphic transformation. So, these are the polymorph transformation, polymorphs of zirconia, that is cubic, tetragonal and monoclinic in the descending order of the temperature. We will discuss those things at a later stage, because zirconia is one compound which has a very important properties, both from the point of view of electrical properties as well as from the mechanical properties. Okay. So, mechanical properties, it is the tough ceramics, one can toughen zirconia by what we call the transformation toughening. So, these polymorphs can be designed properly, the microstructure can be designed in such a way that the materials becomes quite tough. It is not so brittle. In fact, the very first research paper come out on zirconia, so far as the toughening is concerned. At that time people talked about ceramic steel. So, it was equivalent to a steel, applications of steel or metallic materials can be replaced by zirconia. So, on the other hand, zirconia also has a very interesting electrical properties. It is one of the very few oxides having oxygen ion conductivity, a very high level of oxygen ion conductivity, and that is again very useful from industrial point of view, extensively used industrially for many different purposes, we will see at a later stage. So, zirconia is a very important member of structural ceramics, the advanced ceramics materials. Well, coming back again, we have discussed while during the structure many a times we were talking about the symmetry, symmetry in the distribution or the atomic arrangement of the different materials. Let us try to look at it very briefly. What are the different crystal systems available? Sometimes we talk about hexagonal crystal structure, sometimes cubic crystal structure. We have also discussed about monoclinic, for example, in zirconia. So, there are different kind of symmetry elements, and it may not be possible to discuss everything here. However, very briefly let me tell you, there are 7 crystal systems. Okay. There are 7 crystal systems depending on what is the relationship between the 6 parameters, what we call the lattice parameters. 6 parameters in the sense, if you have a 3-dimensional picture and a 3-axis system, A, B, C, or say x, y, z axis, and along the x, y, z we have unit vectors called A, B, C. So, then you have different ways of expressing this volume. Okay. The symmetry may be different in different structures. So, alpha, beta, gamma are the angles between B, C, C, A and A, B. Okay. So, these are the axis, you can see these are A axis, this is B axis and this is C axis. So, alpha is the angle between A and C, beta is the angle between A and B, beta is the angle between B and C, and alpha is between angle between A and B. Okay. So, these are A, B, C axis, and alpha, beta, gamma are the angles between them. So, if that be so, you can imagine various different relationship between them, and this is what we call the triclinic system. The list I will give you in a minute. What is the relationship between A, B, C and alpha, beta, gamma. So, you have triclinic system, you have monoclinic system, and then again monoclinic has two different forms. One is called the primitive form and the other is called base center form. Well, in all these cases, in the corners are occupied by the atoms or ions. Okay. There are all the corners are occupied by the atoms or the ions, and in addition in some of the cases you have extra ions or extra atoms, like in this case it is a what we call base center. Only there are two faces of these two sides, opposite sides are occupied by the two atoms or ions. So, in this case orthorhombic, these are all orthorhombic, 4 varieties are orthorhombic is available. One is the simple or the primitive cell, then you have a base center and then you have a body center here, and then the fourth one is face centers. So, in addition to the corner positions, the face center positions are also occupied by the atoms. So, depending on the atomic arrangement, one can imagine these kind of unit cells, and the definition of the unit cell is these unit cells once repeated in all the 3 different directions completely fills up the volume. Okay. So, and it repeats the symmetry, the vectors are repeated in all the 3 different directions. Here again we have a tetragonal symmetry, and we have only body center, not the others. Okay. In case of tetragonal only body center, in case of monoclinic only base center. Hexagonal, of course, it is a primitive cell, there is no other body center, face center or base center. So, it is only one variety of hexagonal cell, and we will discuss, we will just point out what is the relationship, how hexagonal system is different from cubic or other systems. We have a rhombohedral here, there is no again only the primitive cell is there, there is no base center, face center or body center. In case of cubic, 3 varieties are there. So, it is the primitive, there is no atom inside or either in the body center or face center, whereas this is a face center cubic structure, we have discussed this earlier, face center cubic, and hexagonal we have discussed quite extensively, and there is a body center also we have discussed earlier. So, in all there are 14 kind of systems, what we call crystal systems, or sometimes it is called Bravais lattices. Okay. So, any kind of structures can be described by one of these 14 systems. Okay. So, any structure, any atomic arrangement, whatever you can think of, or actually really in reality whatever exists, they can be described by these 14 Bravais lattices. Okay. And their relationship is given in the next slide, how this x, y, a, b, c and alpha, beta, gamma are related. In the triclinic system, A, B and C none are equal. So, the unit vectors are different. Okay. So, they are completely different, and then alpha not equal to beta, not equal to gamma, and none of them are 90 degrees. So, it is not an orthogonal system at all. So, the angle between any of the two axes is really not 90 degrees, it is different from that, and that is how a triclinic system is described. It is a very least amount of symmetry is available there in this kind of a system, and some of the compounds we will be discussing about the formula of these compounds later on, but these are some ceramic systems like kyanite, basically aluminum silicate, then albite and feldspar. Feldspar we have mentioned earlier, it is one of the major components of or raw materials used in white wares or white clay products. Okay. So, then we come to the second system, it is called monoclinic. The diagram or the axis relationship, the axis has been given in the previous slide. Here it is A not equal to B not equal to C. Once again the unit vectors in 3 different directions are not equal, they are all different. Alpha and gamma, alpha and gamma not are equal to 90 degrees, whereas beta is not 90 degrees. So, that is the relationship between the axis in a axis as well as the angles in the monoclinic system. And the two most important examples are what we call monazite. Monazite actually is a mineral which contains thorium phosphate, okay, and orthoclase is a silicate. Okay. So, these have a monoclinic structure. Orthorhombic, the relationship is like this, A not equal to B not equal to C, whereas all the angles are 90 degrees. Okay. So, all the angles are 90 degrees, but the axis unit vectors or unit lattice parameters are different. Olivine and brookite, there are again two different silicate minerals which have this kind of a structure. Of course, these are only few examples, there are many different compounds which may have orthorhombic structure or any of these structures or symmetries you can say. Tetragonal, A equal to B not equal to C, but in this case again alpha equal to beta equal to gamma equal to 90 degrees. So, all the angles are 90 degree, only one axis is different, A and B is equal, but C axis is not same as AB. So, the two compounds which has this kind of a structure is zircon. Zircon is basically a zirconium silicate structure, ZrO2SiO2, and rutile we have already discussed. So, rutile has a basically a tetragonal structure, tetragonal symmetry. Hexagonal, hexagonal has A equal to B not equal to C, similar to tetragonal, but only difference here compared to any other, you can see alpha equal to beta equal to 90 degrees, but gamma is 120 degrees. Okay. So, it is a slightly different geometry than any of the other one. So, alpha hexagonal has this kind of a relationship between their axis. Sometimes hexagonal is also described in a slightly different way, instead of A, B, C, sometimes is also described as A1, A2, A3 and C. Okay. A1, A2, A3 and C. Anyway, we are not going to discuss the details of that. So, high quartz, one form of silica, high quartz and beryl, and then once again silicate minerals do have a hexagonal structure, but many elements like copper do have hexagonal symmetry. So, many of the metals do have a zinc, copper, zinc, no sorry, I am making a mistake, not a copper, copper is FCC, zinc actually has a hexagonal structure, okay. Copper is FCC structure. Rhombohedral or sometimes is also referred to as trigonal, it is called ABC, here A equal to B equal to C, and then alpha equal to beta equal to gamma, and none of them are 90 degrees. Okay. So, ilmenite, it is another mineral, it is actually iron titanium, iron titanate, that is ilmenite, and calcite is calcium carbonate. Okay. So, rhombohedral is the structure which is available in this kind of compounds, and cubic of course is one of the simplest to describe and the most symmetric material, I think, and where A equal to B equal to C and alpha equal to beta equal to gamma equal to 90 degrees. So, there are many oxides, only two of them have been given here, magnetite and garnet. Garnet again a general formula, there are many varieties of garnets. Okay, so that is the 7 crystal systems, and they apply to any, whenever we are discussing any crystal structure, they will follow or they will have one kind of systems will be fitted into that system, into that structure. Well, now I come back once again for the discussion on silicate structure. It is one of the most exciting and very interesting subject so far as the structural features are concerned. This I discussed last time. Basic unit of any silicate structure or silica is SiO4. That means a silicon is coordinated tetrahedrally by oxygen ions. So, this is a unit which actually repeats itself in many different ways. Okay. So, it has a unsatisfied bond of 4 or unsatisfied charge of 4. So, SiO4 with 4 minus. So, this is the basic unit of any silicate structure and even silica glass. Then they can be combined in different ways. So, two silicon can share one oxygen and the other oxygens can be available for binding to other cations. Okay. So, silicon is being shared or a oxygen is being shared by two neighboring silicon ions. So, then this becomes one unit, okay, and the formula will be Si2O7 6 minus. So, it has 6 negative charges which can be satisfied by combination with other cations other than silica. It may be aluminum, it may be magnesium, it may be calcium. So, some of these things will come and join and satisfy the unsatisfied bonds here. It can form a ring of this nature. Silicon, two silicon ion once again is sharing an oxygen, and out of the 4 oxygen 2 are actually shared. Here none of the oxygens are shared between silicon ions, whereas here one oxygen is being shared by 2 silicon ions. In this structure 2 of the 4 oxygen ions of each tetrahedron is being shared by silicon. Okay. So, there is a ring formation, what we call a 3-member ring formation, and the overall charge, unsatisfied charge is 6 minus. So, Si3O9 6 minus. Then we have a slightly bigger ring. Here is a 6-member ring, instead of a 3-member ring one can have a 6-member ring, and this can be a repeating unit for the other cations to join in and form the total structure. So, here once again 2 of the oxygen ions are still shared by silicon atoms, silicon ions, and the overall group formula is Si6O18 with 12 negative charges. So, more number of cations can join in and form a much bigger molecule. Instead of forming a ring, still 2 of the silicon ions, 2 of the oxygen ions can be shared by silicon in this forming a chain. So, it is called pyroxene structure, and here again we are 2 of the 4 silicon oxygen ions are being shared by silicon, and rest will be connected or joined to bonded to other cations. This is another structure. Again the basic unit is silicon oxygen tetrahedron, and you can see it is what we call a double chain, and this is one chain, and this is another chain, and then there is a kind of cross linkage. Okay. Here this oxygen is shared by silicon of one chain with the silicon of another chain, and as a result in this 4 oxygen of this particular tetrahedra, all the 3 are shared. Okay. This is shared, and also this one is shared between 2 neighboring silicon ions. Okay. So, in this particular tetrahedron all the 3 are shared, whereas next one only 2 are shared because there is no cross linking. So, cross linking is being done at certain intervals, not all of them are cross linked between the chains. So, both kind of 2 bridging ions, 2 bridging oxygen and 3 bridging oxygens are available for the different tetrahedrons. So, effectively 2.5 out of 4 is actually shared, and this particular structure is called amphiboles, and the unit formula is about, depending on what is the number of tetrahedron in a chain, you will get a value of n there. So, it is variable, so there will be different kind of structures or minerals having different kind of formula. These are all summarized here, and this we have started with this. Then we have two silicon on oxygen tetrahedra shared, the 3 member ring, 6 member ring, single chain and double chain. Okay. So, the same thing are being summarized in this case. This is also another summary, of course an additional structure is also there. Only the additional information is these are called olivines in mineralogical name. These are all beryl, or this kind of structure is available in beryl, one kind of mineral, silicate mineral. Then pyroxene, amphibole have been discussed. The only new thing here is mica. This is seed structure. Okay. These are single tetrahedron, 3, 4, 6 rings, tetrahedral rings, 3 rings, 4 rings. 4 rings we did not discuss, but here is a 4 ring is also possible. 6 rings we have discussed. So, there are different kind of rings. Then you have single chain. This is one view of that, and this is the other view. Then you have double chain. Okay. That also we have discussed. What we have not discussed so far is this kind of a structure. So, this chain extends indefinitely in particularly in x and y directions. So, it is horizontally it is extending in the form of a sheet. Okay. So, sheet structure, this is what we call the sheet structure of silicates. So, you have many different forms of silicates. Okay. You have olivines, you have beryl type of structures, pyroxenes, amphiboles and mica. Okay. Mica is certainly very useful product or useful mineral, and the structure is what we call a sheet structure. Here only 2 structures, 2 of the chains are joined together, whereas in the sheet structure a large number of chains are getting joined together to form a complete horizontal structure of silicon oxygen sheet. So, that is another very interesting property of silica, and there are many varieties of sheet structures. I will give some of them, and the most important sheet structure silicate is kaolinite. or sometimes it is called the compound is called kaolin, and compound is called kaolinite and the mineral is called kaolin. So, that is once again a naturally occurring mineral and is useful, very useful, and one of the major components of traditional ceramics. Most of the white clay actually contains kaolin, and when it is mixed with some iron oxide and other things, it becomes red, but otherwise it is a very white clay, and less is the amount of iron oxide, white is the clay. So, this has a very important structure and it has been studied quite in details. The basic description is like this: it is a sheet structure. So, we have a sheet here, it is a vertical, along the vertical direction, this is not the horizontal thing. Earlier we have seen a kind of planar configuration, this is we are seeing from the top. So, this looks like this, but if we are talking looking from the side, it will look like this. So, it is a kind of civil engineering terminology elevation. So, this is the sheet, these are silicon, there are 3 oxygen on this side and 1 oxygen on this side. Okay. So, 1 oxygen is protruding out here this, and so there is some oxygen, one of the oxygens on this layer, whereas 3 oxygens are on this layer, and in between you have smaller ions, the silicon ions. Okay. So, these are silicon ions. So, this is total is the silicon oxygen layer or silicon oxygen sheet. On top of that, vertically above you have another layer, and in this case the kaolinite formula, the chemical formula is actually hydrated aluminosilicate. So, it has silica SiO2, it has Al2O3 and some hydroxyl ion. So, it is actually a kind of interpenetrating layer between AlOH thrice and SiO2. Okay. So, there are this layer actually is a layer of oxygen, a layer of aluminum hydroxide layer. So, these ions, although they have not been differentiated between this silicon and this aluminum, these are all aluminum ions. Okay. These are all aluminum ions, and this layer is actually aluminum hydroxide layer. So, these are hydroxyl ions and these white ones are oxygen ions. So, in this particular layer, there is both oxygen and hydroxyl. Okay. And another distinctive feature of this structure is aluminum is having an octahedral coordination, okay, and whereas silicon has a tetrahedral coordination. So, aluminum has a octahedral coordination, but not all the anions are oxygen, only it is part of its oxygen and partly hydroxyl. So, both hydroxyl and oxygen together form the octahedron, and in between at the center of the octahedron aluminum ion sits. So, you have a interpenetration or a joint, 2 layers are joined together. One is the tetrahedral layer of silicon oxygen, another is an octahedral layer of aluminum, oxygen and hydroxyl. So, this is the composition or this is the structure, that is why that is how you can describe the structure of kaolinite. Okay. So, it is a layered structure, a double layer kind of thing, a silicon oxygen layer and aluminum hydroxide layer, 2 of them are joined together very strongly, there are ionic bonding. So, these layers are quite strongly bonded, and totally it is a sheet like structure. So, this is the description of kaolinite structure, and mostly they will be available in flaky form. Next, we come to some few more sheet structure. I will not discuss in greater details, but I will give you some idea how this kaolinite structure is different from other seed structures. Okay. This we have discussed. This is your silicon oxygen, this layer, and here is the silicon. This is aluminum, and you can see there are 6, total 6. So, this is octahedron here, this is tetrahedron. Okay. So, this is the aluminum hydroxyl layer, and here is silicon oxygen layer. Now, this forms the unit cell. Okay. Then in the vertical direction this repeats itself. Okay. So, this and this are exactly identical. So, these layers are kind of stacked one over the other and forms the total volume or fills up the total volume. So, this is the basic description of kaolinite structure, and this is our unit cell from the end of the lower end of this unit to the upper end of the next unit. That is your what we call the unit cell dimension in the C direction. This is a C direction, and the seat is in the x and y direction or A and B directions. So, the layer is about 7.2 angstroms, and this layer and this layer are bonded together by van der Waals bond. There is no other chemical bond except a van der Waals bond, and these bonds are very weak bonds. This is very strong bond because they have a ionic bonding between these different ions. So, this is difficult to separate. However, this van der Waals bond is very weak bond. So, this layer can be separated out quite easily from the other one, but they do have some bond. So, they are weak, very weak bond in the C direction, but they are very strongly bond in x y direction. So, these are the different layers, atomic molecular layers of the kaolinite, and that is how it is formed. Compared to that, if you go to mica, this is also a seed silicate structure, but the structure of mica is quite different. Not quite different, it is slightly different in fact. If you look at this geometry and this geometry, you will find this is this top portion here is the exact mirror image of the bottom portion. Okay. This portion and this portion are exact mirror image of each other. So, whereas up to this it is actually kaolinite structure. Okay. It is very close to the kaolinite structure. So, as if two silicon oxygen, two kaolin structures are inverted together and bonded together. So, this is actually a more symmetric structure in the sense this side also you have silicon oxygen, on the top side also you have a silicon oxygen, and in between you have aluminum oxygen hydroxyl. Okay. So, one aluminum hydroxide layer is basically sandwiched between two silicon oxygen tetrahedral layers. Okay. So, they are all seats in the x y z direction, this is extending x and y directions, but in the vertical direction C directions, it is called the C directions, they are actually repeating itself in an inverted manner. Okay. So, unlike kaolinite, it is one layer of silicon oxygen and over that a aluminum hydroxide layer, whereas in mica structure or a what we call a double layer silicate structure, you have one silicon oxygen, then aluminum hydroxide is sandwiched between another silicon oxygen layer. So, two silicon oxygen layers sandwiching the aluminum hydroxide layer, that forms the unit cell, that forms the unit cell. So, you have a much longer or a much larger unit cell, here is about 10 angstroms, and then that repeats Here this unit repeats itself, whereas in case of mica this total unit repeats itself. Okay. So, there are 3 layers. However, there are some unsatisfied bonds, and for that in between you have some large ions. Here is they are joined together by only hydroxyl ions, van der Waals bond, and so they are very weak bonds. Here of course, it is not exactly a van der Waals bond, but in between you have some positive ions. These are alkali ions and they are replaceable ions. Okay. Between the layers they are replaceable ions. These ions are normally alkali ions like potassium or sodium, mostly potassium or sodium, and depending on whether it is a potassium ion or sodium ion, you have 2 different compounds of mica. Okay. In case of muscovite mica, it is potassium and sodium mica is also available. So, these are the difference between 2 layers or 2 different kind of seed silicate structures. One is a kaolinite structure and there is a mica structure, and there are many varieties. There are many varieties of silicates, and there are huge number of silicates available, and most of them are naturally occurring, and one can of course synthesize to some extent, but they are very difficult to synthesize. So, most of them are actually naturally occurring silicate structures. Well, we have discussed just now about the silicate structures, where silica or silicon is getting combined, silicon tetrahedron, silicon oxygen tetrahedron is getting combined with many other cations, but silica as such is also a very important ceramic raw materials, SiO2, where it is all silicon oxygen tetrahedra only. Okay. So, the structure is sometimes called mostly called as framework structure. So, in all the 3 different directions there are only silicon oxygen tetrahedron, and they of course have some crystalline formation, so that you have a very definite crystal structures, very definite geometry. So, these things we will discuss in the next class, because the time is up, and thank you so much.